And here we are in the lab again. And welcome to episode 23. And today we are going to discuss, well, we're going to test part of our hardware. There's only two pieces left to test right now on our prototype board. We got to test our ADC, and we have to test our switched outputs. So today is the switched outputs. Next video is the ADC, because I'm not quite done with the code. I'm almost there, and I want to do a little bit extra for that, because that's the last testing we'll do until we get a new PCB, and I hope to have that soon. But I'm going to try to knock out 3 PCBs at once to save some money, because with the tariffs and everything, I don't know what it's going to cost. But so I need to submit the PCB of the IO board, and I want to make a new main brain. All I want to do is just add in that resistor we added in the previous videos, and take out the reset off of the one IO connector pin and make that the halt. And then the processor on main brain is on the other side of the board underneath the display, and I just want to move it to the bottom and get it to so everything's on the bottom and the display on top. So when you want to troubleshoot or debug something, you just flip it over and you have access to all the lines and everything. And then that'll be, after that, then I'll submit the full Gerbers and code and bill of materials and an assembly video, so that anybody that wants to build main brain can easily do so. And then for a third PCB, I need to take the new front end I developed on this one, on this IO board, and I want to put it onto the motion board that I have, which we will discuss later as well. And then that'll be 3 boards we can stack on together like a sandwich, and connect them with that ribbon cable and see if they all work. So that's down the line. That's a lot of work down the line, but that's what we have in plan. And then, of course, back here is my retro 1993 project that I'm working on to get some videos. But that's behind a couple weeks because I got to get a part from Greece. So, and I don't know how that's going to work either. So anyway, that's the plan. And so let's jump on to the switched outputs and see if they work and how they work, and explore all that stuff. So let's get to it. Okay, so let's go over the circuit for the switched outputs, how we can switch a load on and off using a MOSFET. So we'll go Fusion right here. So this is the circuit. This is the supposed to be a MOSFET. I don't know why it happens to be that way, but that's the symbol that they had available for the IRLM6344 MOSFET. So you can rated at 30 volts and 5 amps. So that should be okay for what we're doing. That should give us. Now, I put a resistor here on the gate to limit current, but with this MOSFET, you don't need one, so it'll probably be a 0 ohm. And then if you want to change the MOSFET to a different type, a different value, then you can change, and you need a current limit on the gate, then you can put one in real easy. So I'm not going to take that out of the PCB. I think that'll be kind of important to have. At least gives you options. All right, so the source is just tied to ground. All right, VSS. And so the drain is tied to, well, the drain gets tied to a diode, all right? So let's jump over to the circuit diagram that's easier to read, and I'll explain it better. So here is the circuit, and in this example, this is just a textbook example. You got 12 volts, in our case 5 volts. So you can see the diode blocks the 12 volts from going to ground. So that forces the current path to go over through the motor and then the ground. So the motor, the load, acts as a resistor here so it doesn't go to an infinite current, right? So you turn on the gate here with the 3.3 volts, turns on the MOSFET so it conducts through here. So that connects the negative side of the load to negative VSS or ground, whatever you want to call it. And that completes the circuit. So when this is 0, the MOSFET's turned off. So this is basically open here. So no current flows through the motor. All right. So it's pretty simple, and it's a great example of how to use a MOSFET to switch the load on and off. So that's what we got over here. It just looks a little different the way it's drawn out here. All right. So I put in a socket, a 3-pin socket here. So you will bring in the load, the voltage load, supply voltage for the load, and the positive side of the load plugs in here, and they're basically together. You could do it outside and just run one wire in, however you want to do it, and then the negative side of the load is tied right here. So it's the same as our circuit, just looks a little bit different. All right, so that's how we're switching an external load on and off. All right. Okay, so let's go over the setup real fast. So I got a fan right here. This is our load that we're turning on and off, and it's on switch 0, output switch 0. All right, so the other ones aren't hooked up. I mean, they're identical, so all you have to do is just test the digital value at these ports where it goes into the gate of the MOSFET, just to make sure the CPU is actually toggling the bits. So, and that's all good. So we just want to test our circuit that we just looked at. So that's the way this is hooked up. This wire right here, that's the 5 volts coming in. This red wire's this 5 volt supply to the fan. It's a 5 volt fan. And this is the common ground. And you can see the diode and stuff right here. And the LED port, I have the LED port hooked up to show the status of the data received by the I/O board. So when it reads the memory location for the data, and it displays it right here telling us which switched output is being switched. All right. So if switch 0 is being switched, then the LED 0 comes on or off, depending on its status. If it's on, the LED is on. If switch 1 is switched on, LED 1 is on, and 2 and 2 and 3 and 3, just like that. All right, so it's pretty simple, but we got to test it. That's the way it works. All right, so let's go to our Windows app and check it out. Open up the app, connect to mainbrain, utilities, peripheral commands, switches. I have the board address jumper on 2. If we double click and send that over, then there's nothing gonna, we're not gonna see anything happening because everything is 0. So if we click switch 0, that's with our fan, double click, And there's our fan. See, our fan turns on. And you can turn on any one of these that you want. And you can see the LED lights up to match. And you can turn any one off that you want. There's our fan. It takes a little while to spin down. There we go. And so just click these off. And there we go. We have it. All right. All right. That's a successful test. Okay, so let's take a look at the code that makes all this happen here. So let's see. Let's start at the app, the Windows app. So this is when you select the switches part in MainBrain over here, or in our app, right here, switches. When you click on that, it does this work up here, up above in the command handler, the Windows message handling part of the application. But for us, we just want to do this section, the actual data handling for right now. Well, there's plenty of time later. We'll go over the whole program and stuff on the MainBrain video series. So when you double click on this, then it executes this code right here. All right. So the first thing it does, it gets the window text from the address edit box, which is where we put the address. Then it sends, it loads the data buffer at location 0, offset 0, with 6C, which is the command to get sent to MainBrain. All right. So, because this program communicates directly to MainBrain. So anything else, the data has to go through MainBrain in order to get to any of the peripherals. All right. So this is where it checks to see if the checkbox is checked. So if it is checked, this is a Windows command, a Win32. So if it's checked, then it loads a 1 into data buffer offset 2. It sets that bit 0 in offset 2. It's an 8-bit offset, an 8-bit variable. So then if it's unchecked, then it clears it. And then if checkbox 1 is checked or unchecked, then it does the same thing but 2-bit 1 instead of 0. So checkbox 0 is represented by bit 0 of the data buffer offset 2. This is an array, 64-byte array. And then it goes on down. Each checkbox has its own bit. So it's 0, 1, 2, and 3 bits. All right. So it checks to see what is checked and what isn't, and loads it into data buffer offset 2. And then it calls this function right here, USB byte out, which I'm making it like a global so that a lot of other routines use it, but right now only for the peripherals right now. So that's it right here. So basically it writes it uses the WinUSB write pipe function to write 64 bytes to the USB port, and if it fails, then it sends a message box pop-up saying that it failed and then returns to the program. So that's pretty much it. It writes all 64 bytes of the data buffer, and even though we're only using 3 bytes, the command is always byte 0, offset 0, and the address is always offset 1. And then you have all the upper 62 bytes to play with. And for this, we only use offset 2, byte 2. So then it sends it all over to main brain. All right. So now we come over to our code. So this is 6C. That's the command coming in from our application, Windows application. And so the first thing it does is it calls this right here. And all it does, it gets the current board address, which is in our address. So the receive buffer is a mirror image of the data buffer on the application. So data buffer byte 0 is the same as EP1 receive buffer 0. All right. So it's all EP1 RX buffer 1 is the address of the board, the one that we put in the edit box on the app. So it gets the current board address, and then it just sends the 64 bytes to the SRAM location associated by that board. All right. And then it returns. All right. So we were up here at line 750. Nope. Yeah, well, I wasn't, was I? I'm lost. Right here. All right, so 6C is right here. So it writes the 64 bytes SRAM, then it calls, it sets this global variable right here, and then terminates. All right, so it's that routine is done. So then the main routine of main brain comes down here. These are all underscored because over here we have IO board as the main project, and they have different commands. So as while this is our main program loop. So when this bit is set, then it runs this command, then resets the bit to 0 so it can do it again later. So byte to peripheral function is this one right here. And this is where it does the fancy write, handshake, IO cycle that we talked about in the previous video. So I'm not going to go over this because we already did that. So then we'll go over to our IO board section. And so it gets the command 6C. So up here, as we went over before, when it gets that interrupt saying the data is ready for it, it reads its address 0 for a command. All right. All the peripherals will do that, regardless of what they do or what their function is. So they read the command at address 0, and then I display it on the LED port so we know we're getting the right command. And in case something doesn't work. And the idea of this is to show that we got the data all the way through the system to the IO board. It was received properly, it read from memory properly, and now it has to do a case switch on the value of M data where it read from the SRAM. All right, at address 0. All right, so it comes down here, and these are all the different commands that we went through before in previous videos. So now this is our new one, our 6C command, right? So 6C, if you look it up, is 108. So the same command propagates through the system so it doesn't get confusing, because you don't want a command for the application program sending a command to main brain, and then it gets translated to a different command to the IO board, and then it gets translated. You don't want all that. You just want it to propagate right through the system. Make it simple, no confusion. There's already enough confusion as it is when you write a program. So then it comes down here and it reads our offset 2. Remember our byte 2? It's the same thing with the 64 bytes. It goes all the way through the USB, through mainbrain, into the SRAM, and the I/O board reads the SRAM and it's exactly the same image of 64 bytes. So offset 0 is the same through the system. All right. So then it does a conditional check of M data. Okay. So if bit 1 if bit 0, but it's a 1, so it checks to see if M data is a 1. All right. So by ANDing, so if bit 0 is a 1, then there'll be a 1, right? So if it's a 0, it'll be 0. Okay. So this is kind of shorthand notation for a conditional check to see if true. So this is the value you get if it's true, and this is the value you get if it's false. Okay. And then it checks each one for the checkbox. So that's the bits that we built in our Windows application, propagates through the system, and it still applies here. All right, so checkbox 0 is a 1, checkbox 1 is a 2, checkbox 2 is a 4, checkbox 3 is an 8. So that's bit 0, 1, 2, 3. All right, and then I just display it on the port again to make sure we're getting the right command. All right, which overrides what was written earlier to the LED port. All right, kind of like cascading style sheets. It just cascades over the top of it. All right, so then that's it. It just turns on this bit, which represents the gate of each MOSFET, and that's the program. And then it terminates and does its handshake and releases the system back to mainbrain. Okay, so now we know the I/O switching works, how it works, and everything involved in that. So that leaves the ADC, and we'll do that next.